Hi, in this video, we're going to continue our discussion on how memory is managed in SQL Server. Unfortunately, this is going to be a fairly short video because, as some of you may know, we are in lockdown, so I don't really have all the resources I normally have. So if you remember from the previous video, we were talking about how the memory clerks resize the volume of memory available to them depending on what other processes are running in SQL Server. For example, if you remember, I was loading data into an in-memory OLTP table, and as I loaded data into that table, we saw how the buffer pool shrunk. In this particular video, I'm going to try and explore a little bit about how buffer pool in itself allocates pages, and we're going to do that by executing a query and seeing the difference between serial memory versus parallel memory, desired memory versus required memory, and how parallelism has an impact on memory utilization. So stay tuned. Okay, so let's get started with how memory is granted inside of SQL Server. And in this particular case, I'm just going to quickly brush through some of the topics because I want to show you the demonstration more than the theoretical aspects of it. So the first thing you want to keep in mind is that there is a process through which SQL Server grants memory. And the first step, as you can see in this diagram, is we start with the compile memory, which is right over here. The compiled memory is basically the memory allocated to the query at the time that the query execution plan is being generated. Now, while this is happening, SQL Server is also parallelly going ahead and trying to identify if a plan already exists in the plan cache, which is the second step over here that you see. But rather than wait to first identify if there is a plan in the plan cache, SQL Server tries to do both of these things parallelly. And if it identifies that there is a plan in the plan cache, it'll just release the memory that has been allocated for compile. Now, the compiled memory is actually going to be a fairly huge chunk of memory initially, because that's the kind of like a scratch pad through which SQL Server creates all the permutations of how it'll do the joins, or whether it's supposed to do a scan or a seek. So to identify all the different ways that it could execute the query, it needs a sufficiently large volume of data. So let's assume that this is the first time the query is being executed, in which case we will have the compiled memory, which is used to generate the execution plan. Once the execution plan is generated, then we save that execution plan inside the cache memory. And that's your SQL plan cache, where we look to identify if a plan with the same hash already exists. And if it exists, we reuse that plan. If it doesn't exist, we create a new one. We're going to be talking about that in a lot more detail in a future video, where I'll explain to you the difference between stored procedures and ad hoc plans, and how tools like ORM tools and Hibernate, etc., impact query performance and can be a significant factor as far as memory and CPU utilization is concerned. But that's in a later video. So assuming that this is a stored procedure or some other basic ad hoc query, we'll assume that if we start off with the compiled memory, which is used to generate the execution plan. Once it's generated, we store it in the cache memory. Now, once it's generated in the cache memory, what happens is SQL Server looks at that plan to identify, is there anything in this query that requires me to grant memory to it? So at this point, what you need to understand is that there is already some amount of memory that has been allocated to the connection, and that's always going to be available. The question here is, should I grant more memory over and above what has already been granted? And the reason why we want to worry about that is because when we do things like sort or group by, those are pretty resource intensive operations, and in order to ensure that they complete quickly, we want to be able to store that information in the memory. So when we check for memory grant, we're basically looking in the query to see, do we have a join? Do we have a group by? Do we have an order by clause? Do we need some kind of temporary space in which the data can be aggregated? If this particular memory is granted insufficiently, that's when we have the tempdb spill and tempdb spool, those kind of situations where SQL Server has to offload some of the calculation, the temporary data into the temp tables because there is not sufficient memory allocated within the RAM itself. But assuming that we have plenty of RAM, SQL Server moves on to the next step, and that is to come up with a serial plan. Now, the idea here is SQL Server will always first start off by creating a serial plan. A serial plan is a plan that uses one CPU core or one thread basically, and it estimates if one CPU was running this query, how much memory would it need? And naturally, because it's only one CPU, SQL Server would usually allocate a smaller volume of memory to it, depending on the needs of the query itself. There's actually a fairly big calculation behind that, but we don't need to worry about it in this context. The idea here is that SQL Server starts off with calculation of how much memory would a serial plan require. When it does this calculation, it comes up with two specific values. The first one is the serial plan required memory. The required memory is the bare minimum memory that this query requires in order to run. Simply put, if this bare minimum memory is not allocated, if the required memory is not allocated, the query will not run. The intention here is that If I have that required memory, then I am comfortable with offloading some of the other operations to tempdb, or with a little bit extra RAM that may be lying around. But I cannot do anything until I have the required memory, and that's what that required memory is about. Now, the required memory is the bare minimum, and the desired memory is the ideal. And desired memory basically means if I could do all the operations in the RAM, how much memory would I need? And that's what desired memory is. So you can see it's basically the difference between the bare minimum you need to survive versus what you would prefer. Think of it like a salary negotiation, correct? So before you go for an interview, you'd probably have two values in your mind. One that you definitely will not go below as far as an offer is concerned, and the other one is something that you think you'll be comfortable with. And SQL Server identifies what is the bare minimum, and it identifies what's the desired memory, and it actually uses the desired memory to request to the resource 74. So the resource 74 is the guy who actually allocates the memory. So SQL Server goes ahead and sends a message to the resource 74 saying that I would like to request a certain amount of memory, and majority of the time that requested memory is going to be the amount that's allocated for the desired memory, correct? And wherever possible, if you don't have memory pressure, what you'll find is that the requested memory and the granted memory and the desired memory are roughly going to be the same, correct? Now, once this serial plan is generated, we have an idea about how much effort it will take to execute this query. And at that point, we know the cost of the query. Now, you might be familiar with a property in the server, which is the cost threshold for parallelism, which is the limit at which SQL Server decides whether it needs to consider parallel plans. And if you cross that limit, if the serial plan that you generate exceeds that threshold value for cost threshold of parallelism, then SQL Server goes one additional step and starts coming up with a parallel execution plan. Now, in the parallel execution plan, you can obviously go ahead and configure the maximum degree of parallelism at the server property level or even within the query hint. But having said that, if you've not specified it anywhere and you've left it at defaults, SQL Server looks at the current resource constraints on the system and approximates a value that it thinks it will be comfortable with. So ideally, while SQL Server might have maybe, say in this case, 12 CPU cores, and majority of the time, if you're not facing any memory pressure or CPU pressure, you might actually see all 12 threads being used. But if that's not the case, if there's a thread that is either sick or if there's a thread that's already having a high load factor, then SQL Server might ignore that thread and bring down the number of degree of parallelism for that particular query. And this is going to be important because we're going to talk about that later on. So when it comes up with parallel execution plan, you can see again SQL Server has to calculate what is the bare minimum required memory for a parallel plan and what is the desired memory for the parallel plan. Now, in this case, this is a very rare scenario where Microsoft SQL Server has actually been a bit lazy as far as estimating the memory is concerned. If you've watched the previous videos, I've mentioned that SQL Server usually is very diligent about the way that it allocates memory. So you'll find that SQL Server does a lot of proactive calculations and things like that to get that tuning perfect as far as the amount of memory it requests. But when it comes to parallel plans, what SQL Server basically does is it takes the serial memory, the serial required memory, and just multiplies with the degree of parallelism. And it takes the serial desired memory and multiplies it with the degree of parallelism, as you can see here. And by doing this, the challenge that you'll face is that if you have a system with about, let's say, 12 CPU RAM, CPU cores, that's not really that big a chunk of memory that you might be allocating. But what if you have one of the production systems where you've got 120 cores and then there's parallelism being executed on it? On those kind of situations, you might find that SQL Server over allocates memory unnecessarily just because it lazily calculates the amount of memory simply by multiplying the value that the serial plan requires with the degree of parallelism. So in this particular scenario, you might want to be aware of the fact that parallelism may not necessarily be good for you simply because it over allocates memory. And we'll talk about that in the when I start showing you about the memory grant info within the execution plan itself. So let's try to understand a few other things as far as this is concerned. So I've already mentioned to you the role that the cost threshold of parallelism plays. If the cost threshold of parallelism is exceeded, that's when SQL Server decides to do a parallel plan. Unfortunately, when SQL Server decides to do a parallel plan, it takes the serial memory that was supposed to be allocated and just multiplies it with the number of threads in the parallel plan. So you might actually over provision a lot of memory. And that's why that memory grant feedback feature that we have in the new versions of SQL Server comes into play. There's going to be a video about that dedicated to just that coming up pretty much the next video basically, right? So that's what degree of parallelism has an impact as far as execution is concerned. Now, if you look over here, I've also got in this PPT, you can see that I've got a fairly straightforward select statement. And in the select statement, you'll see that I'm actually executing a query, but at the same time, this is not a very complex query. There is no sort, there is no group by, there's really nothing. It's just a table scan. And because it's just a table scan, you'll see that the output of this particular query is serial memory required 0, serial memory desired 0, memory granted 0, max memory used 0, because whatever memory it already has is sufficient to do the job. There is no request for granting additional memory. Now, having said that, you might ask the question, then what about a large query, a query that's fetching millions of rows of data? So if you look over here in this execution plan, you can see that again, I've got actual rows of about 34 million rows being fetched from the table. And even though there are 34 million rows being fetched from the table, you'll see that I've got maximum degree of parallelism is equal to 1. And you'll see that the serial, desired, granted, and max memory is pretty much 0. So the question that I'm trying to answer here is that the size of the data or the volume of data being fetched does not really have that much of a role as far as the memory grant info is concerned. There is a caveat to this, which is column store, where naturally by default in batch mode parallelism happens. But if you're just fetching from a standard relational table and 8 kilobyte data page, then you'll see that there is really no provisioning happening for memory grants. So it doesn't really matter how large the volume of data is. And the way that you want to keep this in mind is, if you're familiar with integration services, you have blocking transforms and non-blocking transforms. And a non-blocking transform is the one where the data just flows through like a data pipeline, and whatever little memory it has is just being used like a queue where you got a first in, first out. So there is enough memory to do that job, and it's able to keep up with the volume of data passing through. Therefore, a small amount of memory is enough even for a non-blocking transform. But a blocking transform like a group by or sort operation requires a sufficient RAM to store all the data in the memory to complete the sort operation before it can give the output. And therefore, for those kind of scenarios, you want sufficient amount of memory allocated. And in this particular query, as you can see, we don't have that situation, which is why it's okay. And this is an example of a group by, where you can see again, I've got a group by, I'm fetching a sufficiently large volume of data. You can see about 34 million rows over here, and I'm aggregating it by delay type and calculating an average. So in this case, what you can see here is, again, I've got 4 CPU cores on the system, but SQL Server has decided to use only 2 of them. And you'll see that the serial memory is 3072. So for a serial execution plan, SQL Server has decided it needs only 3072 kilobytes of RAM, whereas the desired memory is 3104. So you can see in this case, the serial and the desired is roughly the same. Not all that big a deal, but for larger volumes of data, when you're doing like group by across a very large chunk of data, you might actually see a much bigger difference between the serial required memory and the desired memory. Now, if you look over here, serial, so that's your serial single threaded operation. And then you have required memory, which you can see in this case, because it's maximum degree of parallelism 2, which means it's using 2 threads, you have 6184, which is technically double of this, correct? There will be a little bit of an overhead, but it's usually the serial memory multiplied by the degree of parallelism. And you can see that's what's asked. You'll also see that it desired 6184, it desired 6216, and it requested 6216, and it was granted 6216. And this is mainly because there is no memory pressure in my system at the moment, and therefore there is sufficient memory to grant, and so it was granted. Basically, there was plenty of RAM available, and so that's why it happened. But the important thing to note here is, if you look, you'll see that even though 6216 memory was granted, the memory that was actually used was 1512, correct? And the maximum memory for this query is about 1.9 gigabytes. Now, this maximum query memory is potentially how much memory this one query could use at the time that it was started. You'll never actually reach that limit because there are a lot of other limits that are being enforced internally, but this is basically calculated on the basis of the total server memory and the available memory. And it's saying that potentially if this query needed, there was 1.9 gigabytes of RAM available, but at the same time requested was 6216 kilobytes, so that's basically 6.2 megabytes, and it was granted 6.2 megabytes, but it actually used only 1.5 megabytes. So you can see in this particular scenario, we have that situation where we have over allocated memory, and that's not necessarily a bad thing, because this is all roughly ballpark initially. So the idea here is, statistics and all those things come into play to decide what these numbers are supposed to be. So it's never always going to be perfect, but if you have something around like we have here, where it's about like 20 to 30%, we should be okay. You don't want it to be too much of a difference between what was granted and what was used, because then we have the automatic memory grant feedback kicking in, which will adjust the allocated memory the next time around. But I'll be talking about that in a lot more detail later on. So these are the high level entries that you need to keep in mind whenever you're executing a query. So just to recap, serial required memory is the bare minimum that a single set threaded operation of this particular query will require. Serial desired memory is what it would ideally require in a single threaded operation. Required memory is basically the serial required memory multiplied by the degree of parallelism. Desired memory is pretty much serial desired memory multiplied by degree of parallelism. Last requested memory is if this query was executed before, then it'll have the last requested memory, otherwise it's 0. And then you have the granted memory, which tells you how much memory was actually granted. So you can request for maybe something like 6216 and you may have been granted only 4102, which is a scenario where maybe sometimes a spool might happen to tempdb. But as you can see, this query is perfectly fine. There's not much going on over here, so we're good to go. And that's kind of the overall stuff that you need to keep in mind from the execution plan. Next, I'm going to run some queries and show you this behavior and how the cost threshold of parallelism, etc., comes into play with in the context of the memory assignment. So stay tuned for the demo. Okay, so let's quickly do 2 demos to kind of demonstrate all these concepts that we just talked about. So the first demo I'm going to show you is basically about what happens between a serial plan and a parallel plan. So if you look over here, I've got this query. I'm going to first go ahead and set the cost threshold for parallelism to 50, which means that this query that I'm running here, which is a bit resource intensive, is going to end up doing parallelism. So let me go ahead and show you that really quickly. So it's finished executing. Let me show you the actual execution plan, and you can see there is parallelism going on and there's a RID lookup. We don't need to worry about the details of the execution plan itself, but you can see that there is parallelism. And if I go into the execution plan, you can see that the maximum degree of parallelism is 12, and you can see that we've got used threads 12, reserved threads 12, and the serial memory is only 512, but the desired memory is 730, which is kind of the stuff that I mentioned earlier, that it doesn't always have to be similar. There can be a big difference between what the serial memory and the desired memory is, the required memory and the desired memory is. Now in this case, as you can see, what we have here is we have 12 as the degree of parallelism. So we take 512 and multiply it by 12. So let me go ahead and do that really quick. 512 multiplied by 12, and you can see we get 6144, which is close to the memory that we get here. And a similar thing happens here with the desired memory. We multiply it by 12 and we get this value. Correct. So you can see that because I don't have any memory pressure on the system, the desired memory for parallelism is what gets requested, and you can also see that that's what get allocated. So this is kind of the point that I was trying to drive home with regard to parallelism, where when you do parallelism, you multiply the number of the degree of parallelism with the serial memory that's required. Now what I'm going to do is I'm going to go ahead and change the max degree of parallelism over here to 500, which is a pretty big value. So I'm assuming that this query, when I run it again, is not going to go into parallelism anymore. So when it finishes executing, you can see that there is no parallelism operator anymore. So if I go into the execution plan now, you can see that the degree of parallelism is 1. You can see that the memory grant is 7 megabytes approximately. And that's basically because right now you can see we got the serial memory is serial required memory is 512. The desired memory is 7.3 MB. And because there is no parallelism, you can see that basically the serial desired memory is what gets requested and also what got granted. And that's kind of the point that I was trying to drive home, that when you do parallelism, if you're not careful, you overcommit memory due to the parallelism operator. And a more detailed example of that is coming to you in a minute. So let me go ahead and show you this query now. So in this query, what I'm doing is, as you can see here, I've got select star from, and I've got a fairly small set of data which I'm running. So when I run this query, you can see I'm ordering it by delay minutes, and we get about 16,000 rows. And in this query, there is no parallelism as such. The query is fairly straightforward. And if I go into the execution plan and look at the XML, you'll see that we've got a maximum degree of parallelism 1. We got 512. We've got approximately 3 megabytes. And this is again pretty much similar to the example that we were talking about earlier, where a fairly small query with a fairly low volume of data is requesting a certain amount of memory and getting the amount of memory that it needs, and so everything is working fine. But see what happens when I run this query. So you can see here now this seems to have fairly bigger gap as far as the volume of data that's being fetched is concerned. So it's executing. We'll just give it a minute. And while it's executing, now that it's done, let's go ahead and look at what's happening here. Again, we got max degree of parallelism set to this value, correct? Okay, so let me do this. Let me change the max degree of parallelism back to 50 and run this. So that parallelism actually occurs. So you can see when the parallelism occurs, you can see how we have a sort operator with a spill warning right now. And you'll see that the spill warning says that it was granted approximately 221 MB and it used up 21 MB. So the question then becomes then where do we get 21 MB? So let's see here. This is the parallelism operator. So that means that we have the desired memory at this, which is 113 megabytes, not 21. And you can see that it was granted 133 MB. And if it was granted 133 MB, the question then becomes that where is the spill happening? And here the important thing to keep in mind is that this 133 MB that we're seeing is spread over 12 processors, or 12 cores basically. So you want to divide this granted memory, which is 133 by 12, and when you do that, you'll end up with approximately 10992, which is 10 MB per CPU thread. So you take this 10, take this 10, take this 10, and add it all up, and that's how you get the request for the granted memory. Now the important thing to understand here is that it is these two guys here who spilled. All the others, if you see, they were granted about 10 MB of memory, but they utilized only about 6. It's only these last two guys over here who were granted 10 MB and used all 10 MB. And the rest of the data that these two threads were using were the ones that got spilled into tempdb, correct? So that's why you get the message over here, which let me just go ahead and show you really quick. It says that it was granted 21984 kilobytes and it spilled 21984 kilobytes, correct? So that's kind of the idea as far as that query is concerned, where we're basically telling SQL Server how it spilled over the data, correct? And so you can see this 10 plus this 10 combined together is the 21 that we're talking about over there. And between these two guys, they were allocated a certain amount of memory, but that wasn't sufficient. It used up all the memory that was allocated to those two guys, and therefore it spilled. So the point that I'm trying to make here is that if you look at this detail, you'll actually get to know exactly where the problem areas are. And that helps you kind of figure out how you want to troubleshoot the issue. Now you might be wondering why we have 13 threads. So one is the coordinator thread, which kind of like launches all the 12 threads over here and gets them to do the work that they're supposed to do. So it's kind of like I guess like a map reduce, where the master kind of like sends instructions to the slaves and get them to do the job and then get the data back. So that's what's happening over here. And this is usually the guy that also accounts for a majority of your CX packets wait type as well, because this guy is just waiting idly while the remaining 12 threads do the job that they're supposed to be doing. But that's again CPU related, so we don't need to worry about it at the moment. You can see here details about the spill. So you can see that it was granted 21 MB, it used up 21 MB, and therefore it wrote 855 times to the tempdb. And that gives you details about how close to a spill you are. So if this is not that big an amount as far as we're concerned. So if you had real memory crunch, you might have seen a much bigger number here, which would indicate that no matter what, there was not going to be enough memory to do the job in the first place. But this hopefully gives you a better idea about how you want to understand the execution plan within the context of memory allocation. And what we'll be doing in the next video is I'm going to try and explain a little bit more about the memory grants, which is basically this portion here. It's a new feature, but it's something that would handle a lot of these issues for you on your behalf. So the idea being that while you understand these concepts, you probably don't need to understand them as much, because SQL Server automatically adjusts the memory that's been allocated, and therefore this becomes one less thing for you to worry about as a database administrator. But having said that, it's important to understand the thresholds at which this feature kicks in or doesn't take any action, so that you know when you should start getting involved in the whole process. And we'll go ahead and talk about that in the next video. I hope you've enjoyed this video. I promised it was going to be short, but unfortunately, I usually have a lot to talk about in this topic, so it dragged on a little longer than I expected. But I am hoping that the information in these videos are proving helpful and helping you understand how your query impacts the overall execution. For example, in this particular query, you can see that this query takes a significant amount of memory, and when it's been executed in a report where we have 200 users executing the query simultaneously, and if it's not a query that is already cached in the plan, a single query itself can become a huge resource drain as far as memory is concerned. So that's pretty much it that I wanted to talk about in this video. We'll talk about more details later on, and thank you for watching.